Unit 5 deals with projectiles. And projectiles are very common. Any object that moves through the air is projected, and once you let it go, it continues moving because it's in motion, following Newton's first law. So it continues moving by its own inertia. And the only force that acts on that projectile once you let it go is the force of gravity. So you can see by looking at this free body diagram right here that if we were to draw a box showing our projectile, the only force on it would be the downward force of gravity. A couple terms that you need to know is the path that a projectile takes, whether it's any of the three that you're seeing here, is given a special name that's called the trajectory. And we could be talking about the upward motion or the downward motion or any point through that trajectory. And the shape that you see here, it uses the math term called a parabola. What this slide shows is if you shot a cannon and the cannonball came out and became the projectile without gravity, it follows just a straight line path. And if you notice, the spacing between the ball at every second is exactly the same. It travels at a constant speed. An object in motion stays in motion. When you add gravity, you get the second path, this nice trajectory or this parabola. But the interesting thing to notice is that the horizontal distance that it covers is exactly the same, because gravity only affects projectiles in the vertical direction. Horizontally, there is no effect at all. So although projectile motion can be very complicated, we simplify it by looking at the two components of the motion. So the velocity is actually made up of two parts. It moves horizontally, and it also moves vertically. And what's important to remember is each component is independent of the other, meaning one has absolutely no effect on the other. If the horizontal component was larger, it doesn't affect the vertical component because that's affected only by gravity. So if we look at the vertical component by itself, knowing that it's affected only by gravity, the acceleration is always going to be a negative 9.8 meters per second squared. Negative indicating that it's down, and the 9.8 showing that it's the acceleration due to gravity. As an object moves upward, the velocity is going to decrease because gravity is slowing it down. At the top, if you notice on this picture, there is no vertical component at all. So the velocity vertically is 0 at the top, and then it will increase, try spelling that right, increase on the way back down as it's moving in the same direction as the gravitational force. And if we were to launch an object from this height and check its velocity at this height, its initial and final velocities would be equal in magnitude, but opposite in direction. So the speeds are the same, the velocities are equal but opposite. Horizontally, the motion is much simpler. Once it leaves your hand, there's absolutely nothing you can do to it. There are no forces acting on it. So there is zero acceleration, absolutely none. And the velocity remains constant the whole time. That's important to remember when we study these equations. The horizontal component, the velocity in the x direction, stays the same the whole time. And you can see that by the size of these arrows. Always pointing in the same direction, exactly the same size. So going back to our cannon, you can see here that horizontally, 20 meters per second, the whole time it never changes. Vertically, because it's going down, our velocity is getting larger and larger and larger by about negative 10 meters per second every second. Acceleration due to gravity. So when we go to do the mathematical analysis of projectile problems, we have to look at the two motions independently. So horizontally, we always refer to that as motion in the x direction, has one equation, dx equals vxt. And all this is, it goes back to our triangle from the very first unit of physics, the distance, rate, time triangle. And since we're talking about only the horizontal motion, oh, there's my dog. Since we're talking only about the horizontal motion, and that is not affected by any forces, d equals v times t. When we're talking about the vertical motion, or motion in the y direction, we can use any of our free fall equations. So anywhere that there's a g in here, g will be a negative 9.8 meters per second squared. And when we're talking about these VFs and VIs, so if anytime we have a VF and a VI, we're talking about things that are in the y direction. Okay, two more terms that you need to know in order to study projectiles is when we talk about the distance x, or the horizontal distance, it's common to use the term range. So we're talking about the horizontal distance here. And if you look at the diagram, you can see that when we launch it 15 degrees, the cannonball goes a short distance. At 30 degrees, it goes a little bit further. At 45 degrees, it goes further still. But then something very interesting happens. At 60 degrees, the distance starts getting shorter. And at 75 degrees, it is shorter still. And if we ever went to 90 degrees, this cannonball would just go straight up and straight back down. So it turns out that the same range comes from two angles that are complementary. And that just means they are equal to 90 degrees. And 45 degrees will give you the greatest range. So the greatest distance happens at a 45-degree angle. So we're talking about dx that way. If we're talking about dy, the word we sometimes use is altitude. And if you think of dy as being high, and those two words being synonymous and rhyming, that'll help you remember. And looking back at this diagram again, you can see the bigger the angle, so as the angle goes up, it's going to take longer for that projectile to hit the ground, so the time will also go up. And also think of this as squirting a hose. If you hold it at a small angle, it goes a small distance and hits the ground quickly. But as you start lifting that hose higher and higher, increasing the angle, the water's in the air for a longer and longer time. Okay, so a couple multiple choice questions here. If we launch a projectile at a 15-degree angle, so 15 degrees, what other angle would give it the same range? Well, we know that same range comes from two angles that add up to 90, so the answer is 75 degrees. Question 2. Two projectiles are fired at equal speeds but different angles. One at a small 30-degree angle, the other at a much higher 60-degree angle. They have the exact same range because they add to 90, but which one will hit the ground first? The 30-degree angle, because it does not have to travel as far. It does not have to go as high in the air. Okay, this problem shows three projectiles, red, green, and blue. And if you look carefully at this picture, you'll notice that they have a couple things in common. Number one, they all start from the same beginning point, and they all seem to achieve the same height. So question A wants to know which one would be in the air the longest. Well, it turns out the right answer is C. And the reason is that since they all achieve the same dy, and the time in the air is determined by how high you go, it's controlled by gravity, they all achieve the same height, they all will be in the air for the same amount of time. Question B says which one has the greatest initial vertical component, meaning which one has the greatest up velocity. And once again, the choice is C, because they all achieve the same height, the same reasoning as question A. And question C, which one has the greatest initial horizontal component? This answer is A. Because the blue has the greatest dx, it also had to have the largest vx, followed by green, and the shortest one would be red. Okay, next we're going to work a series of questions that all tie into each other. Start with number 1 here. We are throwing a rock 15 meters per second horizontally. And that word horizontally is very important because it tells us that it's in the x direction, and it's meters per second, so it is a Vx. So our Vx is 15 meters per second. And we know that we're looking at a time of 1.5 seconds. How fast is the rock falling? We are looking for its VF. Now for the beginning of this chapter, our initial y velocity is going to be 0 until we get further along in this chapter and start dealing with angles. So we just have to pick an old projectile equation that has VF. The VI is 0. We know that we have gravity involved and we are working with T. So plug in your variables and solve for your VF. We should get a negative 14.7 meters per second. Negative because it's a negative 9.8, and it makes sense because the rock is going down. The next question is looking for how far has the rock fallen. How far indicates it's a distance, and falling is in the y direction. So our dy equation for projectile motion with an initial velocity of 0 is just 1/2 gt squared. So using your time, solve for the dy. You should get a negative 11.03 meters. The next question is how far, so distance, has the rock moved horizontally, dx. The only equation for dx is vx times t. We know that our vx was 15 and our t is 1.5. So simply multiply those together, and we get a distance of 22.5 meters. Question 6 is taking the last two answers for your dy and your dx, negative 11.03 and 22.5, and putting them together in our right triangle that we were used to using in the previous problem. And when we're looking for how far is the rock from your hand, if we started here, we are looking for this dotted line distance. So what you need to do is do the Pythagorean theorem and then do your inverse tan, making sure you look at your quadrant, and we are in quadrant 4. And if you work that correctly, we should get about 25 meters at 333 degrees. Question 7 is now talking about the entire trip. How long does it take to reach the bottom? We're looking for time for it to fall. Well, all we really know is a Vx of 15 meters per second and a dy of 44 meters. But because this rock is falling, we'll make it a negative 44 meters to indicate that it's going down. So our Vx equation is not useful to us if we don't have one more variable. So we have to go to our dy and do the 1/2 gt squared again, solving for time. Plug in your variables. T squared. And solve for t, and t should be right around 3 seconds. Question 8 is looking for how far, distance, from the cliff does the rock land. So when we were up on this cliff and we threw it off, we are looking for this horizontal distance, so dx. And dx equals vx times t. We'll use our vx, and you have to use your time from the problem that you just worked. And it goes about 45 meters. Okay, question 9 is a very common or very typical projectile problem where you're going to have to use both of your equations, your dx and your dy equations. So dx equals vxt, dy equals 1/2 gt squared. And generally you have to solve one equation to get a variable, generally time, and plug it into a second. So we need to figure out what our variables are that we have. A ball rolls with constant velocity across your 0.95 meter high lab table, and that word high needs to stick out. That is your dy. And because it's falling, we're going to make it a negative, which means our other distance, it hits the ground 0.352 meters from the table. That is your dx. We're looking for how fast was the ball rolling. That's the velocity. And you roll horizontally. So Vx is what we're looking for. But before we can solve for Vx, you're going to have to use your dy equation to solve for time. And then plug that time into the Vx equation. So go ahead and try it. Pause this and then check. 0.8 meters per second is how fast that ball was rolling. This next problem is very similar. You have two distances. Figure out which one is your dx, which one is your dy, and we are once again are solving for Vx. So use the steps that you used for number 9, and go ahead and give this one a try. .7 meters per second. Next, we have another multi-part problem. While standing on a balcony, a child tosses a penny horizontally at 3 meters per second. Meters per second, it is a V. Horizontally, it is an X. The penny hits the ground 1.5 seconds later is our time. How high is the balcony? High, we're looking for dy. So we're going to use our 1/2 gt squared equation, inserting time, and solve for the dy. And although this will come out negative, we're going to make it a positive answer because we're looking for the distance in the upward direction. About 11 meters. Continuation, what was the penny's range? If you remember from before, range means dx. So this is just simply multiplying your Vx and your t, and it goes 4.5 meters. All right, question 13. How fast, velocity, was the penny traveling horizontally right as it hit the ground floor? So we're looking for Vx. This is where your knowledge of projectiles comes into play, because Vx never changes. It's not affected by gravity. And once that penny leaves the child's hand, horizontally, she cannot do anything to it. So it started at 3 meters per second horizontally, and it will continue for the whole trip. How fast was it traveling vertically as it hit the floor? Don't be misled into thinking, oh, it hit the floor, it must be going 0. Just as it hit the floor, it had a Vf. So we need to find an equation that will allow us to solve for that, and probably the easiest one to use is Vf equals Vi plus Gt. And it would be appropriate, if we were talking about velocity, to give this answer as negative. But since I didn't indicate, if you left it as a positive 14.7, that would be okay too. All right, for these next ones, we're looking for what is true. So I'd like you to pause and read through all of them, and then I will give you restart the video when you think you've marked them, and I will tell you the right answers. Again, take a moment to read through these, which are true about the horizontal motion in the x direction. All right, 10 choices here. It's going to take a little bit longer to read, so please pause, read through them, and then check your answers. All right, and one last time, read through these 4 choices that deal with the time of flight. Once a football is kicked at an angle at the very top of the path, remember on the way up, vertically the velocity becomes 0. So at the top of the path, its velocity is entirely horizontal. At the very top of the ball's path is acceleration. The acceleration is entirely vertical because it depends only on the acceleration due to gravity. Okay, question 21. Same thinking is applied. The only force on a projectile is the gravitational force. So the net force is entirely vertical. When is the horizontal component, or the Vx, the smallest? Well, Vx never ever changes, so it stays the same throughout the path. At what point is the Vy the smallest? The Vy gets smaller and smaller as the projectile goes up, and bigger as it comes down. And at the top, the Vy is 0. The next question deals with the demo that we did in class. And if you're bored and you want to watch something, you could look on Netflix for the Mythbusters clip that proved this exactly what we're going to talk about. A bullet is fired from a gun that is held horizontally, and at the instant the bullet comes out, another bullet is dropped to the ground. And the question is, who hits the ground first? Well, it's tempting for our minds to go, wow, this bullet that came out of the gun is going so fast, it's going to take a long time for it to hit the ground. Well, in reality, they hit the ground at the same time, because gravity, frankly, doesn't care how fast you go horizontally. The minute both bullets are released, whether it's from a gun or from your hand, the gravitational force is the only force on them, and they will hit the ground at the same time. This next question refers to another demo that we did in class. If you picture that you're riding in a car, not a convertible, I just happened to use the convertible in the room, but maybe in a bus or an airplane, an object that is moving, could you toss a ball straight up into the air? Well, it turns out that as you are moving forward, you have a velocity, the ball has a velocity, the car has a velocity, and when you toss that ball into the air, it continues moving forward. So that ball makes a nice parabola, and it will land right back in your hand. However, if while you were tossing that ball, the driver of the car stepped on the brakes, the ball is going to land in front of you, because the ball is going to stay in motion following Newton's first law. But if the driver floored it and stepped on the gas instead, the ball would end up landing behind you. Applying that thinking to this problem, if you were hanging a ball out of a bus window and you let it go, bus is going 10, you're going 10, the ball's going 10. So as the bus is traveling along and you're hanging out, the bus will move forward and the ball will move forward, and the ball will land right underneath your hand as it hits the ground. And the path that is seen by someone outside the bus is what we see right here. It is a parabola. A very popular physics problem deals with what's called the monkey and the gun. And I'm not going to shoot an actual gun at this monkey. I have a banana cannon. So what's going to happen is the minute I fire this cannon, the monkey lets go of the branch. So the monkey falls, and I'm going to try to figure out where should I aim at this monkey. Should I aim right at him? Should I aim above him or below him? Well, if I fire this cannon, it's not going to travel straight to the monkey because gravity is going to take over. And that gravitational pull is going to cause that banana to fall. And the monkey's going to let go and also fall. And they both fall under the influence of gravity. So I should aim directly at the monkey.